All right, let's dive into a puzzle that happens right above our heads, pretty much every day. It's about something we all see, but the science behind it? Well, it's the exact opposite of what you'd probably expect.
Okay, so we all know the basics, right? Condensation, like the sweat on a cold drink, happens when things cool down. So here's the big question. Why do the biggest, fluffiest clouds seem to pop up on the absolute warmest, sunniest days? It feels like it shouldn't work that way. And that's the puzzle we're going to unpack right now.
So here's the secret. It's actually not about the heat we're feeling down here on the ground. The very same sunshine that's making the day hot is also kicking off this incredibly powerful cooling process, but it's happening way, way up above us. And that's what we've got to get our heads around. To really get what's going on up there, let's bring it back down to Earth with a couple of super simple examples. First, a bike pump. You've probably felt this, right? As you pump, the barrel gets surprisingly hot. That's because you're compressing air, and that creates heat. Now for the flip side, a spray can. Use one for more than a few seconds, and the can gets icy cold. Why? Because the gas inside is expanding really fast. Hot pump, cold can. It's the same principle.
Now, this whole process has a bit of a fancy scientific name, adiabatic temperature change. But don't let the name scare you. All it means is that the temperature is changing without adding or removing any heat from the outside. It's not like putting it over a fire or in a freezer. The temperature change is happening just because of changes in pressure.
So let's boil it all down to one simple golden rule. This is the key to everything we're talking about today. When you compress air, it warms up, and when you let air expand, it cools down. That's it. Remember that?
Okay, to see this rule in action in the real world or, well, up in the sky, we're going to do what meteorologists do. We're going to imagine a little invisible bubble of air. They call it an air parcel. And we're going to follow this little guy on its journey straight up. All right, our journey starts down here on the ground on a nice sunny day. The sun's beating down, heating up the earth, and that heat radiates up, warming the air right above it. So our little air parcel gets warmer and less dense than all the air around it. And what happens? It starts to rise, just like a hot air balloon. So as our bubble of air climbs higher, the pressure around it starts to drop. I mean, there's literally less air sitting on top of it, less weight pushing down. This gives our parcel room to stretch out and expand. And hey, what was our golden rule? When air expands, it cools down. Now, this cooling process is surprisingly predictable. It happens at a very specific, very constant rate that we call the dry adiabatic rate. And that word dry is super important here. It just means the air isn't saturated yet. There's no visible cloud, it's still just clear air. And get this isn't some tiny temperature drop. For every 1,000 meters our little parcel of air climbs, it cools down by a whopping 10 degrees Celsius. That's a massive cooling effect, and it's driven purely by that expansion. No freezer required. Okay, so our parcel just keeps on going, rising up, expanding, and cooling down at that steady 10-degree rate. But it can't just keep doing this forever. It's heading for a critical point in altitude, where the rules of the game are about to change completely. And that tipping point is called the lifting condensation level, or LCL for short. This is the magic altitude. It's the exact spot where our air parcel has finally cooled down to its dew point. At this point, it's totally saturated. It just can't hold any more water vapor. This right here is where a cloud is born. So as soon as we hit the LCL, this amazing chain reaction kicks off. First, boom, we're at saturation. The air can't hold another drop. Second, that invisible water vapor starts to condense into actual tiny liquid water droplets. And third, and this part is a huge game changer, that process of condensation releases a bunch of hidden energy. We call it latent heat. Think of it as the energy the sun used to evaporate the water in the first place, and now it's being released back into the air. Okay, so what does releasing all this heat do? Well, you can think of it like a tiny heater just switched on inside our air parcel. The parcel is still rising and expanding, which is trying to make it cooler, but now you've got this little burst of heat fighting back against the cooling. And the result? The cooling rate slows way, way down. And of course, this new, slower cooling rate has its own name too. We call it the wet adiabatic rate. The wet part is your clue that we're dealing with saturated air now. A cloud is actively forming. So yeah, it's still cooling as it rises, but just not as fast as before that cloud started to form. I mean, you can really see the difference here.
The dry rate is locked in, it's a constant 10 degrees. But the wet rate, it's always less, usually somewhere between 5 and 9 degrees per 1,000 meters. And the reason it varies is just because it depends on exactly how much moisture is in the air, condensing and releasing all that heat.
So this really breaks down the journey of our air parcel into two totally distinct parts. On its way up, in the clear, unsaturated air, it's cooling down fast. That's the dry adiabatic rate. But the second it hits that lifting condensation level and cloud starts to form, bam, the brakes get topped and the cooling slows down to the wet adiabatic rate.
And there you have it. The puzzle is solved. That heat on a sunny day doesn't directly make the cloud. It's just the engine that gives the air the initial push to start rising. The real magic, the powerful cooling that we need, comes from the air rising, expanding into lower pressure, and cooling itself down from the inside out. It's an incredible process. So now you know about the invisible engine that literally paints the clouds across our sky. But that brings up a whole new question, doesn't it? What's the difference between a little puffy fair weather cloud and a towering massive thunderstorm? What decides a cloud's ultimate fate? Well, that's a whole other story.